You can extend a Lewis structure theory by applying what's called VSEPR. VSEPR stands for valence shell electron pair repulsion theory. And it's a really cool way to figure out the geometry of the molecules you're looking at. And the punchline of all of this is that electrons want to be as far apart from each other as they can. So in the upper right-hand corner there's like those two kind of lobes looking things. Those represent pairs of electrons, all right? And they're both negative, and they want to be as far apart from each other as they can. So they're going to be 180 degrees apart, one totally opposite each other. In the middle of the lobes, that would be the central atom, all right? So that could be a carbon or a nitrogen or whatever. And if there are two pairs of electrons around it, they want to be as far apart from each other as they can. So the whole thing of VSEPR, electrons want to be as far apart from each other as they can.
According to VSEPR theory, the valence pairs surrounding an atom move to positions that minimize their repulsions.
If you have two lone pairs, they want to be as far apart from each other as they can. That would be 180 degrees. If you have three lone pairs, they want to be as far apart from each other as they can. That would be 120 degrees from each other. But if you have four pairs, then you do something else, which is a little strange. I'll show you some stuff here in a little bit. I do want to highlight this guide right here, which is called the Geometry and Polarity Guide. We're going to be talking about a lot of different names that are used to describe these geometries, and I've tried to compile all of them in this guide. So I do recommend that you get a printed version of this that you have next to you. You can answer these questions as we go through this here coming up. So if you have two pairs around a central atom, they want to be as far apart from each other as they can. And a great example of this is beryllium difluoride, BeF2. So the F atoms want to be as far apart from each other as they can. They're going to take up 180 degree positions. And this would be a linear relationship. The FBEF angle would be 180. That keeps the fluorines as far apart as possible. So in that rotating sphere right there, the middle of those two lobes, that would be the beryllium, and then the lobes represent the two fluorines, and they want to be as far apart from each other as they can. Sometimes, though, you have a central atom with three pieces around it, like boron trifluoride we looked at earlier. Boron trifluoride, those fluorines want to be as far apart from each other as they can, and they will be farthest apart if they are in what's called a trigonal planar geometry. So the fluorine-boron-fluorine angles are all about 120 degree angles. This is a flat molecule. So BF3 is actually flat, and we would describe the angles as 120 degrees. Now, when you add a fourth one, it might be tempting to say that, oh yeah, they would all be at 90 degree angles. So if you had a flat molecule with four pieces around it, it would be 90 degrees as the angle between them. But what really happens in three-dimensional geometry is instead of a 90 degree angle, you can get them a little further apart if you place them in what's called a tetrahedron. So notice that there's an example of a molecule, for example, CH4, and the carbon in the middle has four hydrogens around it. And instead of having them at 90 and 180 degrees, you can get more separation if you put them in a tetrahedron. So you can think about it like you have one on the top and three on the bottom. That's kind of a cheesy way to do it, but it works. But again, the advantage is you keep those lone pairs, those bonding pairs, farther from each other. Each of those CH bonds, again, is just a big thing of electrons, and you want to keep them as far apart from each other as you can because electrons don't like being close to other electrons. So 109 is better, farther separation than 90 degrees. That's why the tetrahedron dominates when you have four atoms around a central atom. If only they would have been able to keep it at 90 degrees, there's lots of things that we would have avoided as chemists, but alas, Mother Nature likes to keep them as far apart as possible. Tetrahedral wins over 90 degrees and 180 degrees. So let's go back to the ammonia structure we looked at earlier. And ammonia was a nitrogen with a lone pair and 3 bonding pairs. And let's describe this molecule now using VSEPR, okay? So what you would do is you'd want to count the total number of bonding pairs and lone pairs. And so around nitrogen, you have 3 bonding pairs to hydrogens and 1 lone pairs. So 4 pairs total means that that nitrogen is going to be in a tetrahedron, or it's going to be in a tetrahedral geometry. One of the positions will be that lone pair, which is on top, and the other 3 positions will be hydrogens. So chemists would describe the electron pair geometry, the EPG, as tetrahedral. The H and H angles are all about 109 degrees. Sometimes chemists like to talk about, though, what's called the molecular geometry, which is the geometry of what the molecule would actually look like if you could shrink yourself down to the level of the molecule. Now, lone pairs are just shimmering electrons. We saw in the last chapter how the electrons are actually just random kind of orientations. You wouldn't really see them or anything like that. So the molecule then would look like a 3-sided pyramid. Chemists would call the molecular geometry a trigonal pyramid. So if you have an electron pair geometry which is tetrahedral and one of the positions is a lone pair, then the molecular geometry is called trigonal pyramid because it looks like a 3-sided pyramid thing. Let's apply VSEPR rules now to the Lewis structure for water. Now, water is H2O. Notice that hydrogen is listed first. Hydrogen sometimes is listed first. We'll talk about this more later. It's listed first a lot of times for acids and things like that. For whatever reason, hydrogen is first. But anyway, when you draw the Lewis structure, you'll find that oxygen is in the middle. Hydrogen can't be in the middle. It always has to be on the outside. The oxygen has 2 lone pairs and 2 bonding pairs, so it has its octet. It's totally happy. But for us here now with VSEPR, what you want to do is first count the number of bonding pairs and lone pairs around your central atom. And oxygen has 2 lone pairs and 2 bonding pairs, 4 pairs total. So like with ammonia, that means that this is also going to be a tetrahedral electron pair geometry. In water, 2 of the 4 spots around the tetrahedron are taken up by lone pairs, and the other 2 spots are taken up by hydrogens. So if you think about then the molecular geometry, which is what that thing looks like, knowing that the lone pairs would be invisible but still present, you're going to end up with an HOH angle, which is bent. It's going to be about 109, which is what at the time you see most of the time with tetrahedron. So for water's geometry, then, we would describe the EPG, electron pair geometry, as tetrahedral, and the molecular geometry as bent. That's about 109 degree angles right there. So let's apply VSEPR rules to sulfur dichloride, SCl2. What would be the molecular geometry of SCl2 specifically? So when you draw the Lewis structure for SCl2, the sulfur's in the middle of the chlorines. The sulfur has 2 lone pairs and 2 bonding pairs around it. So if you count up the total pairs, that's 2 bonding plus 2 lone pairs, 4 pairs total. That's going to be tetrahedral. But tetrahedral is the electron pair geometry around the sulfur. So we know that all of those angles will be about 109 degrees or so. So to figure out the molecular geometry, we look at just the bonding pairs. There's 2 of them. And in a tetrahedron, the bonding angles are always about 109. So believe it or not, SCl2 has the same molecular geometry as water. The ClS-Cl angle would be bent. It would be about 109 degrees because it's in a tetrahedron. It'll look just like water, except you'd have sulfur in the middle and chlorines on the outside instead of oxygen in the middle and the hydrogens on the outside. So kind of cool. Methanol is CH3OH. Methanol is an example of an alcohol. Alcohol in the chemistry world is a family of chemicals that have an OH on them, and we'll talk more about that in a future lecture. But if you draw the Lewis structure for methanol, that CH3 has a carbon with a tetrahedral environment. So tetrahedron means 4 bonds. 3 of the bonds are to hydrogen, and 1 of the bonds is to oxygen. Then the oxygen itself has a bond pair to hydrogen hydrogen and 2 lone pairs on it. So that would be the Lewis electron dot structure for methanol. Now, you can go farther, though, because anything that's tetrahedron should be about 109 degrees. So if someone asked you what the HCH angle was, angle 1, or the HOC angle is, angle number 2, well, both of those are tetrahedral geometries. And so both of those would be about 109 degrees. And that's kind of a cool thing to know. So you can actually make predictions. Now, a Lewis structure is not written with any kind of bond information at all. So notice in both of those Lewis structures, the HCOH, that's like flat, 180 degrees, right? And the H's are above and below there in that CH3 group. But in reality, you can interpret that using VSEPR to know what the actual angles are. And anything that's tetrahedral would be about 109. Anything that's trigonal planar would be 120. Anything that's linear, 180, blah, blah, blah. So a Lewis structure is great for scientists who can't draw, and I put myself in that list, by the way. You don't have to include any angle information. You don't have to show things and stuff, which is really cool. However, the hip chemist, which is what you should also consider yourself to be, can use VSEPR to interpret the geometry. So that little animation there shows a better representation of what methanol is. And you can see there's kind of cool angles, all about 109 degrees. It doesn't look anything like the Lewis structure, but the Lewis structure can be interpreted to figure out what the molecule looks like. So that's kind of a cool thing about VSEPR. It allows you then to visualize, at least in your mind, what the molecule would look like in the real world. Acetonitrile is a methyl group with a cyanide on it, and when you draw the Lewis structure out, it also has one of those CH3 groups like methanol did, but now it has a carbon-nitrogen triple bond. And the question is, what are bond angles 1 and 2? So bond angle 1 would be the HCH, but bond angle 2 would be the CCN angle. So bond angle 1, HCH, that carbon central atom is tetrahedral. There are 4 bonds around the central carbon right there. And again, anything with 4 bonds will be tetrahedral, and that means 109. But the carbon in angle 2 is kind of cool to talk about because it has a triple bond on one side and a single bond on the other. Well, we're going to see in the next chapter that double bonds and triple bonds are basically like one big cloud. They kind of stack on top of each other. So we saw earlier how if there's only 2 bonds, the bonds want to be as far apart from each other, 180 degrees. Well, triple bonds, double bonds, and single bonds count as just one big cloud, one big bond. So that carbon number 2 in bond angle 2 has essentially like 2 bonds around it. That's going to be 180 degrees. So triple bonds, double bonds, single bonds, they all count as like a big bond, if you will. So that central carbon in angle 2 has a triple bond on one side, a single bond on the other. That's like 2 clouds of electrons that want to be as far apart from each other as they can, 180 degrees. Boron trifluoride, things that go under the octet, can also apply these rules just as well. The boron in the middle and the Lewis structure on the right has 3 fluorines. They each want to be as far apart from each other as they can. That's a trigonal planar electron pair geometry. And those angles are all about 120. So again, note that the Lewis structure for BF3 looks like it's kind of 180 and 90 degrees. And that really is nowhere near what the actual molecule looks like, which is right there. It's more like 120 degrees from each other. So again, Lewis structures don't have to have any information about the actual geometry, but you can interpret a Lewis structure to give what the molecule would actually look like. And if you had drawing skills, which I don't, you could probably draw something at 120 degrees. It's kind of a cool extension, and artists will have a wonderful work of this compared to my poor artist skills. Now, you can go past the octet too, and this is another important consideration. So here's an example of phosphorus pentafluoride, PF5. And phosphorus in that middle there has 5 fluorines around it. So this is going now beyond the octet, and there are absolutely rules to figure that out. So if you have 5 clouds of electrons around a central atom, they refer to that as a trigonal bipedal bipyramid, all right? And a trigonal bipyramid just has 5 electron pairs, if you will, around the central atom. Now, what's really interesting is that when you have a trigonal bipyramid, there's several angles to pay attention to. There's like a middle part, and that's like a trigonal planar geometry we saw earlier, like with BF3. All of those angles are 120 degrees. But then you have a fluorine on the top and a fluorine on the bottom. And if you compare the top or the bottom fluorines to one of the plane ones, those are 90 degrees. But in reality, there's a third angle too, because the F angle that goes right up and down the middle, that's 180 degrees. So these are kind of wild. All right, you've got 3 angles to think about, 90 degrees, 120, and 180, and that'll be important for some stuff we're going to talk about here in a little bit. If you have 6 pairs around a central atom, which is also possible in period 3 and lower, then you get to an octahedron. An octahedron is actually somewhat common. An octahedron has everything at 90 degrees and 180 degrees. So you can see that most of the angles that are listed are 90, but there's also 180 degrees when you go from like the top to the bottom, if you will. So think about 90 and 180 degrees when you think about it. Again, all of these rules are just the electrons trying to stay as far apart from each other as possible. And I'd also like to re-highlight this geometry and polarity guide. It'll have all of these names, the bond angles, even the polarity and stuff listed. I tried to make it a pretty cool guide for you to start learning this stuff and figuring out what's happening. Let's go back to our sulfur tetrafluoride example we saw earlier, where sulfur was going beyond the octet. And that sulfur had 4 fluorines and a lone pair around it. That's what made it go past the octet. Well, if we wanted to figure out the geometry then of it, it would have 5 pairs, and 5 pairs makes it a trigonal bipyramid. So trigonal bipyramid is when you have something above and below a trigonal planar plane. We'll think about 90 and 120 angles like it shows there, as well as the 180 degrees. Now, it is important where the lone pair goes here, because as we talked about, or I mentioned earlier, unshared pairs are bigger than bonding pairs or shared pairs. And so you want to give the lone pair or pairs as much space as possible. And you have a better molecule when you put that lone pair in one of the middle parts right there. In one of the parts that's the trigonal planar, if you will, part. And why that is you want to have as few 90-degree angles with the other atoms as possible. So if you put one there in the middle part, there are 2 90-degree angles, one for the fluorine above and one for the fluorine below. And that's actually better than if you put a lone pair on the top, like if you replace that fluorine with the lone pair. Then you'd have 90-degree angles for 3 different fluorines, and it's better to have just 2. So long story short, if you have a trigonal bipyramid structure with 1 lone pair, it always creates what's called a seesaw. And this picture in the upper right shows what it would look like, knowing that the lone pair, which would be right here, by the way, in the structure, knowing that the lone pair is invisible. A seesaw, if you put it 90 degrees, would have like a kid on the left and the right, the top and the bottom, if you will, fluorines that could go up and down. If you use your imagination, you can see it. If you don't worry about it. But again, that geometry and polarity guide will help you with all this kind of stuff. So 1 lone pair goes on the equator, if you will. It's going to have then a better structure than if you put it on the top. These are the different orientations you can have for both trigonal bipyramid on the top and octahedral on the bottom. So first of all, note the first one on the left-hand side. This is a trigonal bipyramid without any lone pairs, like PF5. Then you have EPG and MG the same. So for PF5, which has no lone pairs, electron pair geometry would be trigonal bipyramid, and molecular geometry would be trigonal bipyramid. It's the same name for EPG and MG if there are no lone pairs. However, if you have 1 lone pair, then it's better to put it kind of in the plane, as we talked about in the last part. This creates a molecular geometry of seesaw. So for SF4, we would say the electron pair geometry is still trigonal bipyramid, but now the molecular geometry is seesaw. If you keep going, the T-shaped, it would be the molecular geometry with 2 lone pairs. And if you have 3 lone pairs, they all go in that central plane. That actually creates a linear molecular geometry. Now again, all 4 of those, the EPG would be trigonal bipyramid, but you do change the molecular geometry name as you add and subtract lone pair electrons. The bottom is for octahedral electron pair geometries. So all 3 of those would be octahedral EPG, no lone pairs, EPG and MG the same. If you have 1 lone pair, it creates the square pyramid. And if you have 2 lone pairs, it creates what's called square planar. So at this point, I need to point out, it's really important, if you've been in other classes, sometimes they'll say like trigonal planar, you can get by with just saying planar. And you can't do that here in Chem 221 because square planar and trigonal planar both have planar in them. So you have to say at least like trig plane or something like that. So I know it's trigonal planar, and square plane, so I know it's square planar. And pyramidal is even worse. You can't say just pyramidal. You have to say trigonal pyramid, square pyramid, stuff like that. Trigonal bipyramid, lots of different pyramid names. So just realize we're kind of in the big kids class. You got to use big kids terms. Don't just use pyramid, planar, stuff like that. It doesn't fly very well in this class.